In this video, you will learn about power functions and polynomial functions. By the end of this video, you should be able to identify a power function and the end behavior of a power function, and identify a polynomial function and identify the degree, leading coefficient, and end behavior of a polynomial function. So to get started, we want to talk about power functions. A power function is a function with a single term that's a product of a real number, which we call the coefficient, and a variable raised to a fixed real number. So we're going to represent our power function in general as f of x equals k times x to the p. So looking at these three functions, which of these are in fact power functions? Well, remember, they have to be a single term. But on this one, you may notice that it's very easy for us to combine these into one term. Well, it actually is one term, but we can combine them as 8x to the fourth. So this is a power function. The second one is not a power function because I cannot combine these, and they are not, because they are not like terms, and I have more than one term. So this is not a power function. And similarly here, I have a function divided by another function. It's not a single term, so it's not a power function. So what do power functions look like? To describe the behavior as numbers become larger and larger, we like to use the idea of infinity, and we use the symbol infinity for positive infinity and negative infinity for negative infinity. We say that as x approaches infinity, we can write as x with an arrow to infinity. Then we're describing the behavior, that's what's happening as x is growing arbitrarily large. So when we talk about an even power function, a positive even power function, we're talking about an even power. What we can say is that x approaches both positive and negative infinity, the function approaches infinity. So the graph here shows three different power functions. Each one has an even power. We have x squared, x to the fourth, and x to the sixth. And what you'll notice is that on both ends, as x approaches infinity, the function values get larger, and as x approaches negative infinity, the function values also get larger. So again, we say as x approaches infinity, the function approaches infinity, and we can say that for negative infinity as well. As x approaches negative infinity, our function approaches infinity. So that's for an even power function. I like to think of that as up, up. For a positive odd power function, on the other hand, so positive odd power, as x goes to infinity, the function goes to infinity, and as x goes to negative infinity, the function goes to negative infinity. So let's take a look at some of those. So we have three different odd power functions here. Notice how the graph flattens out kind of near the origin, and it's steeper the larger the exponent. So what we notice is that, again, as x approaches infinity in this direction, the function values approach infinity in this direction. However, as x approaches negative infinity in this direction, the function values, the y values, approach negative infinity. Okay. So let's take a look at these examples here. The constant in front of the variable will tell you if the graph is reflected across the x-axis. So we know, for example, one of our favorite functions is x squared, and we know that that is going to go up and up. But if I put a minus sign in front of that, it's going to reflect and it's going to go down both on the right and on the left. So let's take a look. We've got f of x equals x to the 7th. This is an odd power function and it's got a positive coefficient. So it's going to go up in the first quadrant, down in the second, and we would describe it as x goes to infinity, the function goes to infinity, and as x goes to negative infinity, the function goes to negative infinity. Our next example is an even power function. And we notice that for our even power function, we have a negative. So normally an even power function would go up, up, but we reflected it, so it's going to go down, down, and we'll describe it as so. As x approaches infinity, the function approaches negative infinity, and as x approaches negative infinity, the function approaches, hold on, I want to take that comma off. The function approaches also negative infinity. For our third example, we have an odd power, which normally would be up in the first and down in the third, but because our coefficient is negative, it's going to be up in the second and down in the fourth. And we'll say, as x approaches infinity, the function approaches negative infinity, and as x approaches negative infinity, the function approaches infinity. Okay, so we now know about power functions and the end behavior. What is a polynomial function? Well, don't let this panic you. A polynomial function in general looks like this. You'll notice you have a sub n, x to the n, a sub n minus 1, x to the n minus 1. What we're doing here, the a values, these a's are coefficients, and the n is a power. And so if that one's n and the next one's n minus 1 and the next one's n minus 2, we're basically saying decreasing order. And our subscripts for our a's relate to the power. So a sub n is the coefficient of the term with the x to the n. When we talk about a lead coefficient, we're talking about the term with the largest power. So our lead coefficient here, our lead term is a sub n x to the n. The lead coefficient is just that a sub n, and the degree is n. So let's take a look at some of these examples here and see if we can't identify the degree, the leading term, and the lead coefficient. And I'm always going to start here with the lead term because that tells us both of the other two. But do remember that these have to be in descending order. So this one here, we have x to the first as our only power there. So our leading term is 3x. The degree is 1, and the lead coefficient is 3. And I'm just going to say positive 3 there because that's really the important part, is its sign. For our next example, be careful. We notice that this one is not in descending order. So if we write it in descending order, we get minus 4x cubed plus 5x squared plus 9x. and our leading term here is minus 4x cubed. So our degree is 3, that's the power, and our lead coefficient is negative 4. For our next example, we have 3x to the 4th plus 5x plus 5. We notice this is the term with the highest exponent, so 3x to the 4th. The degree is 4, and the lead coefficient is positive 3. The last one can be a little confusing. It's a constant function, so it's like x to the 0. So our leading term is 7, our lead coefficient is 7, and our degree is 0. Polynomials have a couple of characteristics. They are always smooth, continuous curves. That means we're going to have some like wiggly things here with no holes and no sharp corners. Okay. And the domain is all real numbers. So let's take a look. Let's make sure that we're clear on the terminology of polynomial functions. We have the leading term, the degree is the power, and the leading coefficient is our a sub n. And when we write it in that descending order, we say it's in general form. So an example might be 5x to the 7th minus 3x to the 4th plus 2x squared minus 5. When we look at a polynomial, we can identify the end behavior of the polynomial graph using the leading term test. This is very similar to the end behavior for power functions. So if we have an even positive power function, it's going to go up, up. And if it's an even negative, it's going to go down, down. It's just that reflection. Similarly, for an odd positive, it will go up in the first, down in the third quadrant, and for odd negative, it will be reflected. So I like to think of these two, well, the top two as either up, up, or down, down. That's how I say it. And for the odd positive or odd negative, it's like a slope. It's a positive slope or a negative slope. So let's take a look. We want to identify the degree, the lead term, the leading coefficient, and more importantly, let's do the end behavior. So it's in descending order, and so our leading term is minus 7x to the 4th. So that's our lead term. Our lead coefficient is negative 7, and our degree is 4. So we have an odd degree and a negative lead coefficient. So this is going to have the end behavior that looks something like this. So we would say as x approaches infinity, the function approaches negative infinity, and as x approaches negative infinity, the function approaches infinity. Let's do that looking from a graph. Can we describe the end behavior and determine a possible degree for the polynomial function? So that second question is the easiest to answer. So when we look at this, we notice that they don't go in the same direction. One goes up and one goes down. So this has to be an odd degree. And since it kind of goes up this way, it's a positive odd degree. The end behavior would be described as x approaches infinity, the function approaches infinity, and as x approaches negative infinity, the function approaches negative infinity. Okay, so if our polynomial is not in standard form, decreasing order, but maybe is in a factored form, we still want to be able to find the lead term, the degree, and the end behavior, but we don't really want to have to multiply it out. So what we think about when we think about degree, that's really the number of factors. So in this case, we have x, x minus 2, and x plus 3. So how many x's do we have? We have 1, 2, 3, 4. So the degree in this case is 4. Our leading term, if we think about just in general, if we multiply these together, we'll get an x squared. And then when we multiply that by 14x squared, we're going to get 14x to the 4th. So this is an even degree with a positive coefficient. So it's going to go up, up, and we will describe it like so. As x approaches infinity, in other words, going this direction, the function values are also going to infinity. As x approaches negative infinity, going in this direction, the y values are also approaching infinity. That concludes this video on power functions and polynomial functions.